Get all the gadgets set up here. Well, we're doing a little experiment tonight here too. We're not using the screen. When we got to Adele, we didn't have a screen to use at all, and we ended up just shooting on the wall, and everybody loved it because of how large it was. So we'll give this a shot and see what everybody thinks. So here we go.
Sistema готовый. 5 секунд до старта. 4, 3, 2, 1.
Well, I'm Zerby, and this is Jim Bonser. We're going to pretend that Sputnik looked like the guy on the screen there. Sadly, he's going through most of what the Russian space program did. It's collapsing miserably. But we're going to talk about robots in space probes, and human exploration of the universe.
Before we do that, though, you've been sitting for a while, so why don't everybody stand up for a second. And I'll have you put your hands up high as you can reach them. Try not to do that. I want you to bring them together hard 5 times, no more, no less. Ready? 1, 2, 3, 4, 5. Okay, good. Sit down. See, I told you we'd get a standing ovation.
That's beautiful. All right. We're done, right? All right. We don't need to give the speech if they're already happy about it. So. Okay, well, the first thing I want to know is how many ringed planets are in our solar system? Everybody just shout it out if you know the answer.
3, 4.
3, 4.
3.
2, 3. Okay, well, let's see what we got here. Well, there's Saturn. Obviously, we know it was the original ringed planet. Uranus. They found the rings for Uranus, I believe, in 96, something like this. So it's a ringed planet. So there's 2. And Neptune. It's a ringed planet. There's 3. Well, not only Neptune, they've now found out that even mighty Jupiter has a ring. Jupiter has a ring system. So is it 4? There's 5. There's 5 ringed planets in our solar system. Most people don't know this. The Earth is a ringed planet. It is the first man-made artificial ring in the universe. Now, the compression on that's a little funny, but I've seen the video. Unfortunately, I couldn't have the video because apparently the military doesn't want everybody to see where their satellites are. But when Cassini was on its way back past Earth, headed out to Saturn, it turned around and took a picture of the Earth. And you could clearly see rings around the Earth of man-made materials. And here's why. Since Sputnik launched, or Sputnik, in 1957, October 4th, 1957, there's 245 probes. Now, these are U.S. probes, have left the Earth to explore our solar system. 26,072 satellites have been launched. 16,000 of which are dead. We cannot control, and the fuel is gone. Now they're locked in trajectory. They're geosynchronous. They're not in danger of falling into the Earth. But 16,000 of these satellites are uncontrollable, but they're big enough to track. In fact, a sugar cube is big enough to track with the computers at Goddard Space Flight Center. And in fact, 660,000+ objects larger than a sugar cube are tracked by Goddard Space Flight Center. There's something like 2,100 military satellites included in all that, and I have no idea how many Russian satellites. So there's been 134 shuttle launches. We're on STS-135 coming up here in July, and 261 Cosmodrome launches. Neither one of those includes the probe launches. You'll find as we go through this, Russia was prolific in launching probes. I mean, anything they could put in a satellite, they were lobbing their lunch into space. They beat us almost 100 times over as far as the number of probes that we launched. So, 2 of these probes have left our solar system. Voyager. And we're going to focus on Voyager 1 here because Voyager 2 pretty much did everything that Voyager 1 did. It was launched first. Voyager 1 was launched second. There's about a month of difference in between them, maybe a little more than that. And this is the Voyager 1 spacecraft here. It was launched in September of 1977. And it was August, actually, and I think about that, Voyager 2 was launched. So they had a month in difference. It has been operating continuously for 33 years, 8 months, and 14 days. And think about that. This is a machine a long way away, made in the 60s, that's still operating today. It is 116.32 AU, which is astronomical units from the Sun or Earth. At that distance, it doesn't matter between the 2 of them. There's 1 AU difference. It's about 11 billion miles. It's funny, if you look online, you'll see these numbers that are not right. Look at the date they were put online. I actually came up with this figure by taking that date and adding the amount of time between now and then and how fast it was traveling. It's traveling extremely fast, 12 kilometers a second. So it crossed the termination shock, and we'll get into what that is here in a little bit, and is now in the heliosheath of our Sun. It should cross the heliopause within the next 3 years. So by 2015, it'll be in this area of the solar system we call the heliopause. And we're broken. There we go. Okay, the termination shock. It is the point in the heliosphere where the solar wind slows down to subsonic speeds. It's so far away that the solar energy just dies off. The heliosphere is basically, it can be defined as the bubble of dominance of the solar system. So anything outside of the heliopause, like we were talking about, it's outside of the dominance. It's where the solar wind blows, you could say. This is a good representation of it here. Here's our planets, even Pluto, which is a planet, by the way. Here's the termination shock. That's the point, like I said, where the molecules from the Sun, the solar energy, is no longer moving forward. It's lost its energy. The heliopause is where all this stuff starts to build up. So if you can imagine, you've got the Sun over here, and it's spinning out all these particles that have the exact same weight at the exact same speed, and when they all run out, they stop at the exact same place. So then you have what's called the hydrogen wall in the bow shock. All this stuff is accumulating out there in a new hydrogen cloud. So the heliopause should be crossed by 2015, like I said there. Important dates. In 1990, Voyager turned around and took a picture back towards the Sun, a family picture of all the planets. It's a little hard to see up here on the screen. And then Pluto was a planet, so it even took a picture of that. But so here, this is the first family portrait, if you will, of all the planets in our solar system. In 1998, Voyager became the furthest item from the Earth, the furthest man-made object from the Earth. It overtook Voyager 2, like I'd said. It took 20-something years to do it. But it did. It slowly, a month's difference in launch. They had different trajectories, but it took 20 years for it to overtake it. So in 2010, December of 2010, Voyager 1 relayed the data that it was finally moving faster than the solar wind. So this man-made object is out there moving faster than particles that are emitted from the Sun. So it'll cross the heliopause in 2015, and by 2020 is when they're going to start a 5-year shutdown process. Each instrument that's not the most important instrument, they'll start taking it down and taking it down and taking it down. It's run by what are called radioisotope energy generators. And by 2025, they will no longer be able to run any of the instruments. So at 2020, they're going to try to maintain it as long as possible. But by 2025, Voyager will be no more. This makes me very sad. I'm 33, and Voyager's been around my entire life. So it's something that I've grown with. That's always been a part of NASA and human spaceflight. So, Pioneer missions. Now, Pioneer is kind of fun. Pioneer was one of the real first pushes into space. And we started out with lunar orbiters. And it's funny because the number's Pioneer 0. You may wonder why Pioneer 0. Well, because it exploded. It never made it off the launch pad. And so they decided, well, we blew up the first one. We'll name what was going to be Pioneer 2, Pioneer 1, and so on. And they just moved them back. So Pioneer 1 became a lunar orbiter. And it missed the moon. And it missed the moon by 1 million miles. Okay, the distance from Earth to the moon is 250,000 miles. So the moon is there, and it went that way. What happened is the first stage malfunctioned, or the second stage malfunctioned, excuse me, and the third stage fired through it, and it was redirected, and it put a little bit of a curve in the trajectory. So we try again. Pioneer 2, another lunar orbiter. Sadly, it exploded. We're not doing so well so far in the early days of NASA. But this time, okay, we're not going to try to orbit. We're going to just launch this object past the moon. It missed again. It went that way. So here, we're 0 for 4 at this point. Exactly, the moon, and so finally they came up and they said, well, let's try this, and they did it, and it worked. And that was Pioneer 4. Was the first planetary flyby, or first extrasolar flyby. Excuse me. Then they came up with this idea, P1. They didn't name it. It was a TV transmitter. They were going to launch this satellite into space and video the moon and send it back to us so we could all see the moon from closer up. It exploded. Right. P3. I don't know what happened to P2. There's no evidence of it. I looked around and it exploded. So we're from 58 to 59. Now look at the time here in between each one of these launches. Okay, now it takes months to get the shuttle ready. We have August of 58, October 58, November 58, December 58. They were just 1 month after another. They were lobbing stuff into space because we were in the space race. We were fighting Russia for top dog. The interplanetary medium satellite was Pioneer 5. They finally decided, hey, we're aiming at the moon and this is not working. Let's just shoot one that way. And they lobbed it at Venus, and it worked. The math was less complicated. They finally got it all figured out. You got to realize that the computers on these things were less memory than the computers in a $1 calculator at Walmart now. So, Pioneers 6 through 9 were launched consecutively in Marches of the years 65, 66, 67, 68. And they're currently up there working today. They are in orbits around the sun, and they're what's called the Solar Weather Network. There was another one. There was Pioneer E, which I believe was Pioneer 10 that got renamed because it exploded. It was also supposed to be part of the Solar Network, but sadly it never made it. So, Pioneer 10, now we're getting into some stuff that really works. Pioneer 10 was the first deep planet explorer. It went out and explored the asteroid belt and the outer planets, the large planets, the giant planets, excuse me. It was launched in 72. It is currently still out there, still working. We lost contact with it in 1995, but it's out there. It's 112 AU. It's not the furthest item out yet. Remember, that was Voyager. But it's moving at 12 kilometers a second. So that's from here to Nevada every second. Roughly. A little more than that, actually. It's headed for Aldebaran. And I was really excited when I saw this. Like, wow, it's eventually this probe is going to make it. So I took 2.6 AU a year. Divided it by the amount of time that it would take, which is 65 light years at the speed of light, mind you. So there's a little complicated math there. And I was like, well, how long is it going to take to get there? And it's exciting because humans will have a presence in Aldebaran in no more than 2 million years. It's going to take a little while for it to get there. But it's headed at Aldebaran right now, which is exciting for me because that's one of my favorite stars, actually. Pioneer 11 was specifically designed to experiment with what they assumed was the heliosphere. They didn't know if it was just a concept at the time, and it actually discovered that this is really what's out there. And it was launched in 73. It was an asteroid belt and heliosphere observatory, and it's moving in the opposite direction of Pioneer 10. Pioneer 10 is headed to Aldebaran, which is out of the galaxy, and Pioneer 11 is headed towards the galactic core. So it's headed towards Scutum. Whoops, you can't hardly see that there, but which is a constellation, and there's a star there that's actually pointed at that has a name about that long. So we're going to ignore that for now. And at 2.48 AU, it's 1.6 million miles away, or million years away. Excuse me. So it'll be a little while before we're recognized out there. Now, Pioneers 12 and 13. A lot of people didn't know there were Pioneers 12 and 13. They were actually Venus probes, and they were what were called bus probes. And they literally were buses. Each one of these probes had 12 sub-probes or mini-probes on it. And when it got to Venus, it just started launching these probes at the planet. And they were very, very successful missions. I mean, I think they put 20 total, including the the parent probes around Venus, and it was a very, very good study of the planet Venus. So, Ranger's fun. Rangers were called moon bombs because we literally were shooting rockets at the moon to see what would happen when they, we wanted pictures and stuff like that. We wanted to see what happened when we hit the moon. We didn't know if it was hollow, if it was just a big dust pile or what. And Rangers were the ones that started to prove this stuff. They were lunar impactors, and they didn't have very good time with these either. This one blew up on the launch pad. I don't have any fun animations for it, but Ranger 1 exploded on the launch pad. Ranger 2 was 61 again, exploded on the launch pad. I think we'd get new rockets by then, but Ranger 3 took off, worked, missed the moon. It's a big object. Don't know how we keep missing the moon. Ranger 4 had a computer failure. It hit the moon on the wrong side. It hit the back side of the moon, so we didn't get much data from that either. Ranger 5 missed the moon. Ranger 6, perfect impact. It launched perfectly. Everything worked. It went great. But we forgot to turn the camera on. So, okay, by Ranger 7, we finally started getting somewhere. We made it. Ranger 7 piled into Mare Cognitum and returned some of the most magnificent video and images NASA has to this day. It's really fantastic to see this. Ranger 8 and Ranger 9 worked. They both made it to the moon. So, 3 out of 9 is not bad. It's about 30%. Should be an A on my finals as far as I'm concerned. Mariner was, as far as the U.S. is concerned, one of the most prolific programs out there. It was a champion of firsts. Each one of these is a Mariner. This is Mariner 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Mariner has many, many different crafts. In fact, as you'll see, there's some surprising twists in the Mariner saga here very shortly. Again, it was a champion of firsts. Only 3 of them failed this time out of the entire program, which was light years better than the previous programs, as you have seen. They were interplanetary probes. They were specifically designed to shoot for Mars, Venus, and to look and to see what we could learn from these other planets by using probes. And then later, they would turn into something that a lot of people don't realize. First planetary flyby, which was Venus, came out of a Mariner. The first pictures from another world, which I believe was Venus, came from a Mariner. First to use gravity assist. Now, what is gravity assist? If we want to go to the outer planets, we have to go to the inner planets. That doesn't make a lot of sense, I know. But we slingshot the spacecraft around the inner planets, and it gains great velocity. And the gravitational forces of those planets then zing it out into the outer part of the solar system. Without gravitational assist, we'd never make it to the outer solar system. But remember I told you those were Mariners, and I'll explain in a minute, but Mariners were supposed to go to Mars, Venus, and Mercury, right? Well, the original 12 missions were Mariners, but 11 and 12 became Voyagers 1 and 2. And it was Voyager that used the gravity assist to make it to the outer planets. Why the name change? Congress cut the budget for Mariner, and back then, all the departments of NASA got along. And so when the budget got cut for Mariner, they decided, well, the Voyager program has gotten started, but they don't have any ships yet. So they underhandedly slid the program over to Voyager, used the funding from Congress for Voyager, and they still were able to use their project. So, the Magellan probes. Magellan was launched in 1989, I believe, which was a Venus probe. It was a Mariner. These things were designed in the 70s, in the late 60s. And in 1989, we used a copy of a Mariner probe, Mariner 9 actually, as the Magellan probe that we sent to Venus. Well, that's 1989. I mean, that was a long time ago, right? Well, actually, the Galileo probe from 1995 was a Mariner offspring probe as well. They took the original design, and you saw the dismal record of NASA. They decided, well, this program worked. These spacecraft fly. So they've used them over and over and over again. But 95, I mean, actually Cassini. The Cassini mission was also a Mariner. So to this day, they used Mariner spacecraft as probe craft. They finally found a program that worked, and they stuck with it. Which is more than we can say for most of the things that NASA does today. They no longer use Mariners. New Horizons is a completely different kind of probe. It's a box probe. It's very, very different. There's no longer the sexy, elegant space probes of the 60s and 70s. They're big cubes. With the exception of James Webb. We'll get to that one here shortly too. Surveyor. Surveyor was a mission to prove that we could land softly. You guys remember the Ranger probes were designed to bomb the moon. I mean, they were meant to slam in. We didn't have any brakes. Well, they gave Surveyor brakes. There were 7 missions, I believe. Yeah, 7 robotic spacecraft that went to the moon that were on trajectory, ballistic bullet paths, and they got close to the moon and they kicked on the brakes. And they hit their descent rockets. They were the first ever spacecraft to have descent rockets. And they slowed down and softly hit the moon. Landed. We won't say hit. They landed on the moon. Now here's a fun fact, though. This is Surveyor 3. And Surveyor 3 was the first robot ever to lift off from another world. But it was by accident. Surveyor 6 was actually designated to be the first human spacecraft to launch from another world, to prove that, hey, if we send astronauts there, we can get them home. Well, Surveyor did it. Twice. The spacecraft gets to the moon, it lands, it's beautiful, and the trajectory computer went, I don't like it here. Fired the rockets, launched the spacecraft back into orbit. It comes back down and lands perfectly. And it didn't like that spot either, so it took off again and landed the 3rd time perfectly. Now you guys remember Ranger and Pioneer. This guy came out of nowhere. All of a sudden it's bouncing all over the place, but it worked every time. So this is Pete Conrad. This is Apollo 12. Pete Conrad is shaking Surveyor's hand. Because without Surveyor missions, Pete Conrad would have never been on the moon. We would have never landed on the moon. Apollo wouldn't have been possible. So that's probably my favorite out of all of this. I mean, here's this space probe doing its own thing. But it worked every time. It might have had a mind of its own, but it worked. Now, in the research that I did for this, originally when Jim and I started talking about it, I said, I want to do all the probes. I want to talk about every probe there was. Wrong. These are some of the probes that I would love to get to, but can't. This is about 1/10 of the list. I have a list at home that I downloaded for Jim and I to go through, and it's probes by year. It's 7 pages long, and that's the programs. So it's very interesting, and you'll notice that the twin rovers that are on Mars are not on here. I've left that out specifically. We'll do another lecture entirely on the twins. There's so much data on the rovers and the Mars programs, that'll be another lecture. So don't gang rush me on the way out because we didn't get to the rovers. I know they're everybody's favorite, but we will. Remember I told you that the Russians were very prolific. Here we've got, U.S. had Viking 1-2, Vanguard 1-7, Explorer 1-49, which was huge. And then I got to Cosmos. Cosmos 1 through 2,441. The Russians were lobbing everything into space they could get their hands on. Some of these are satellites, some of these are weather, some of these are military, but the Cosmos program had 2,441 probes in it by itself. Luna was another program from Russia. It was by far the most prolific lunar program. 24 probes on the moon, and by the way, Russia beat us to everything. First on another planet, first on the moon, first into space. The only thing they didn't beat us to was a human on the moon. Every other record goes to Russia when it comes to space flight. It wasn't really a space race. It was us trying to catch up the whole time. It really was. So these are some of the probes from our past. We'll talk about more of them at another time. But what about what's coming to our future? That robot you saw waving was actually Robonaut 1. It was waving at Robonaut 2 as it left on STS-133 for the International Space Station. As of this day, we have humanoid robots working for us in space. Let's see here. Whoops. Oh, we're missing a slide, it looks like. Okay. Well, Robonaut is a 330-pound humanoid robot that actually is detachable at the waist. You can attach him to the arm, the maintenance arm in the International Space Station. He actually has thrusters in him where he can work his way around the International Space Station on his own. You can put legs on him. You can put wheels on him. You saw one of the packages, Robonaut 1, on a Mars rover. He's very versatile. He has the dexterity of a human. He has more joints than a human, and he has more ability to, more dexterity than a human as far as flipping switches and things of that nature. He can move his limbs at 2 meters a second. That's faster than that. So he can lift about 40 pounds in each hand. And I'm trying to remember the other thing. Unfortunately, the slide's missing here. But he was built as a consortium between General Motors and NASA. And we've got a great video, I'm not going to play it tonight, but of him in the International Space Station. He also has a Facebook and a Twitter account if you guys want to talk to him. He has an actual feed that he sends out that's on Facebook and Twitter. It's not somebody at NASA sending this stuff out. It's Robonaut. And it's kind of neat because they were scheduled, the people in the International Space Station, the astronauts, were scheduled to unpack him at 8 a.m. And of course, if you worked on Robonaut, at 8 a.m. you were at NASA to see this unveiling of your robot. And they unpacked him and the box was empty. And it was the people in the International Space Station. They were playing a trick. They couldn't wait to get him out of the box. So as soon as he came off the space shuttle, they unpacked him. And they panned over. They said, well, we'll go look at this camera. And they panned over to this other camera, and there he is on Facebook. So here's the robot in the International Space Station already working 12 hours before he's supposed to be, and he's on Facebook. So even the robots we're screwed. But so from Robonaut, we have the James Webb Space Telescope. Now this is the successor to our beloved Hubble. We all love Hubble. It's really changed humanity as far as I'm concerned. And James Webb, it'll launch in 2014. It's almost finished. And it's funny because the budgetary cuts actually killed Webb many times over the decadal surveys at NASA. And individual funding and stuff like that has kept it going, and that's what's working on it right now. Government funding has actually been cut for it, but they're still making it through. It will set at the L2 point, Lagrange 2. It'll be about 1 million miles opposite the Sun from the Earth. And it'll have a 365-day orbit too. So it does not orbit the Earth. It orbits the Sun every 365 days. Weighs 14,000 pounds, which sounds like a lot, but it is a third the weight of Hubble. I actually found that quite fascinating myself. It's a 5-year mission to image the edge of the universe. So the whole point in Webb is to see the edge of creation. It was named after the great NASA administrator, James Webb. He was the second administrator and oversaw more launches than any other NASA administrator. It cost $6 billion so far. They figure it'll take between another $1.3 and $2 billion to finish it and get it into orbit. So this is the Webb mirror versus the Hubble mirror. And next to me, and yes, I'm holding a machete. This mirror is 18 segments of highly polished, gold-plated beryllium. It is 6 meters across. It is 6 times the area of the Hubble mirror. It's 6.5 meters across as opposed to Hubble's 2.4 meters. It is enormous compared to Hubble. Here's a cross-section of it actually, and it's 72 feet long. A side ride bus, the big side ride buses are about 50 feet. 40 feet. Well, there you go. So it is as wide, which is 40 feet, as a side ride bus. It's huge. Does anybody here play tennis? Play tennis? Okay. Tennis court is 75 feet long. It is wider and almost as long as an entire tennis court. And I'm throwing all these numbers at you, and I know it might be a little hard to kind of grasp how big it is. It's that big. That is the Goddard Space Flight Assembly crew for the James Webb Telescope. There is 171 people standing in front of the telescope. You could fit 3 times that many people on its solar shield. It is the largest spacecraft ever built. In fact, it's so big. Uh-oh. Well, that's not going to work. That's a video of it unfolding in space, but unfortunately it looks like that's not going to work. This is the assembly room for James Webb. And if you go to this web address right here, and I can send it out to everybody in the club later, and if you're guests, email outreach, and I'll get it to you. You can go to this link right here. Just go to the James Webb website and go to webcam. You can watch them build this. It's actually right here, right now. It's off the screen. I took this picture Friday night after closing time, and a few minutes later the lights actually went down. But each one of these things, this is a mirror. Right here, it's inside this protective case. This is another mirror and another mirror. But you can actually watch them build the telescope. So I'm sure you guys didn't think that you were going to have a quiz today, but I'm going to be a professor someday. So I figured I'd practice on you. We'll see how many people paid attention. What was the first robot in space? Just shout it out when you have the answer. What? Sputnik. That's right. How far away from Earth is Voyager? Who remembers that one? 11 billion miles. No, 32 light hours actually. 32 light hours, 14 light minutes. It's exactly 11 billion miles. Yeah, give or take a few hundred million. But 32 light hours, it takes 32 hours for communication to get there and 32 hours for communication to get back. But we can still control the spacecraft. In fact, as late as last year, they sent a command to it to change orientation, and it did it, and we let it go, and it automatically reoriented. It is fully functional. It's still, everything runs absolutely fine. How long will it take for Pioneer to arrive at Aldebaran? 2 million years, that's right. These I didn't get to talk about, but we'll see if anybody knows what that is right there. What was the first robot on the moon? Now I already told you that Russia beat us to all the first, so you can assume, especially by looking at it, that it's Russian. Luna 2. Very good. Again, a Russian spacecraft. What was the first robot on another world? And by world I mean planet. What?
Surveyor 3.
No. Venera 7. That's right. The first successful mission, we tried, everybody tried, but Venera was the first successful landing. So now Jim's got some near misses that he's going to talk about here. Let me get your slides.
I'm going to talk about, I haven't told you, wow, this is really loud. I bet that'll be a little bit better. Evan told you about a lot of failures that we had, but there were also a lot of almost failures that NASA was able to rescue and actually do some incredible space science with. So I want to talk about just a few of those. How many of you have ever had a plan and had it actually go to completion the way you wanted it to? It doesn't happen that often, does it? And we saw NASA had problems with that too. And I seldom have my plans. I plan my days out and they almost never go the way I expect them to. So NASA had the same issues with some of their stuff.
I love when a plan comes together.
Anybody recognize that? That was the Genesis probe. It's going to return space dust to us. It didn't land very well.
5, 8, 5, 5,
No plan. Right now.
We need a new plan right now, BJ said. So we had a lot of near misses. That one, the drogue chute did not deploy. It did not pull the parachute out, and so the craft tumbled down. But NASA was able to retrieve a lot of that aerogel stuff that was exposed to space and captured little tiny dust particles and meteoroids. And so they were actually able to do quite a bit of science with that probe, even though it basically crash landed. Voyager 2 had a lot of problems, and yet it's probably one of the most prolific space missions NASA ever put out there. Started with its computer. Actually, before it even launched, it had 3 computer subsystems, 2 of which failed 2 weeks before launch. And so they ended up pulling another one of their satellites, redoing a little bit. They have like a spare or a backup ready to go. And they put it in, they launched it on schedule, but in place of the original Voyager spacecraft. Not long after it got up in space, one of the stabilizing gyroscopes started just acting weird. But then after a few hours it straightened itself out. They don't know what happened or why, but they're thankful that it figured it out. Then there were more computer problems. The computer was, let's see, I better look at my notes a little bit because I forget things. Yeah, this one, because it had so many computer problems, I keep them straight. The computer started acting a little bit like HAL on Space Odyssey. They would send commands up, and the spacecraft would reject them and do whatever it wanted to do. And they would send it back, and they kept going back and forth. And eventually, though, that sort of fixed itself too. Actually, what happened was they realized that the engineers had programmed a lot of fail-safe stuff into the Voyager, so that if it was affected by solar wind or by some kind of rotational problem or just the environment in general, it would correct itself. But they made it too sensitive. And so what was doing was they'd issue a correction and it would say no, and it would wildly overreact to the correction. So they reprogrammed, they got that kind of figured out. The science instrument boom, this thing here that has these instruments on it, was kind of folded up against the spacecraft when it was launched because it was in like a rocket casing, and then it was supposed to extend itself out and go out, and then it would lock in place. And when they got the report back, they issued the command, do it. It never came back with a, okay, I'm done command. And eventually engineers figured, well, it seems to be functioning right. We think it actually worked, but the sensor that was supposed to report that it was locked just failed. So then the thrusters seemed to have a mind of their own. They would just sort of fire erratically whenever they wanted to. Sounds kind of like that one lander on the moon that, I don't like this spot, I'm going somewhere else. And so the thrusters had issues, but eventually those sort of straightened out. Filter wheels would jam for the cameras. They would image through different filters for different information. The filter wheels would get stuck. There were even more computer problems. later on, well, take my word for it, there were other computer problems. I can't find it in here. But anyway, in April of 1978, the primary fuses, the fuses for the primary radio blew. They had a backup radio, but unfortunately, just before that happened, they found out that the backup radio had malfunctioned. And so they were having difficulty communicating with the craft. The main radio was out because its fuses were gone. Once the fuses are out, there's nothing you can do about that. And so, but they got the backup radio. It would work sometimes. It was kind of an intermittent problem. And so when they kind of got it working, they quickly uploaded a whole bunch of information so the thing could almost run itself. But then the radio seemed to go just fine. Didn't have any more problems with it, and it's still that's the one that's being used today. So the backup really had a interesting history.
We're losing it out here. So.
Oh.
Yes.
Okay. So that was Voyager, and as we said, Voyager is one of the most prolific missions. It went everywhere. Maybe if I just move this up. Can everybody hear me okay?
Yeah, it's clipping.
It's clipping? Okay, well maybe I should use the other one then. Shut that off. Is this on, Evan, or?
No, there's a little switch on top.
Okay. Okay. We're going to talk a little bit about Hipparcos. Does anybody remember what the Hipparcos mission was all about? Somebody way in the back. Ed?
Star distances and sizes.
Right. Hipparcos was going to try to get more precise information about where stars were, mapping stars, and also the primary mission was to try to measure the parallax of a number of stars. And what that means is, well, they would get on one side of Earth, or one side of the sun, and they would take a picture of the sky, in particular some stars, and then they would wait 6 months, and when we got to the other side of the planet, then we would take another picture, and we'd see the stars in the background would shift a little bit, and the stars in the foreground, or the stars in the background remain constant, but the ones in the foreground closer would shift a little, kind of like when you're driving down the road in the car, and you look out and the fence posts near you are moving by really fast. The trees in a field a little ways away, they're moving by more slowly, because as you're moving down the road, you're changing your point of view, and as you're moving, it seems like the farther you go, the things in the far distance, they don't move hardly at all. Things closer and closer, they seem to move faster and faster. And so you can use that information and do the math and do the trigonometry and figure out how far away something is. Hipparcos was extremely successful in that mission, but took a long time to get there. At launch, the Apogee boost rocket, it's not like Apogee's not its name, but the idea was it was going to send this thing up into a very elliptical orbit to get it out, and then once it got out to the peak, then it was supposed to have another rocket that would boost it and then make it into a circular orbit. It was actually 22,000 miles from the Earth, so it would be a geostationary orbit, geosynchronous orbit. So as the Earth turned once every 24 hours, this thing was out 22,000 miles, also turning at the same rate of speed. So if you looked up at night, and you could see like a good telescope, that we have a new star that just followed us around. All the other stars would move, but that one would stay still. It would be in the right same pot. That's how your satellite dishes for your dish network, or those have the same kind of satellites. That's why you can point that dish antenna at a particular spot and you keep getting your TV signal. Well, unfortunately, the boost engine did not work, and so it stayed in that real highly elliptical orbit. I don't know if I wrote the numbers down. Nope. It went from its 22,000 miles at its farthest from the Earth down to about 310 miles. So it was a really huge elliptical orbit that it was in. So obviously it was supposed to be stationed right over its ground control in Germany. Well, obviously it's in this big orbit, so it's not doing that. It's circling around all the time. And that puts it even low enough that it goes through the Van Allen radiation belts every time it gets close to the Earth, which really messed up the solar panels on the thing and gave it issues. Its primary radio fuse is blue. Occasionally, no, I think that was left over from the previous. Ignore that. This is false data. Spurious data from the old slide I didn't clean up. But in this orbit, occasionally, it would be eclipsed from the sun by the Earth. So it would get behind the Earth, the sun would be over here, the Earth is here, and the satellite's here, and it would stay in that shadow for up to an hour. Well, when it lost power for that long, the solar panels couldn't get enough energy, it would go into a hibernate mode. And so then they'd have to wake it up. And any work it was doing, gone. You know, it lost all its controls, and so they had to go through the routine to wake it up again. So the poor thing was just taking naps all the time. Felt like me. Out of contact with Germany 70% of the time. You know, it was supposed to be stationed right over Germany so they could have a direct line of sight communication with this thing. But because of that orbit, it was stuck in that transfer orbit, it lost contact 70% of the time. Nevertheless, it did way more than it was expected to do. I didn't put a note on there, but the extra fuel, you know, the booster that failed was still attached to the spacecraft. So you got this extra mass on there, full of fuel, a lot of extra weight. So controlling the spacecraft, aiming it, doing everything, took a lot more effort to do. It could be done, but it used more fuel. They had to come up with some really ingenious ways to control the craft, but they were able to do it. And over the 3.5 years that Hipparcos was in operation, it was able to exceed its original mission of measuring star positions, 118,218 stars. It checked the parallax of. In addition, it mapped 2,539,913 stars with unprecedented accuracy. You know, on the Earth we have difficulty because the Earth's atmosphere tends to make things move around, and getting really, really tight measurements is difficult. Photograph to photograph with ground-based telescopes, things will move around. You won't get the precise location that you can get out above the Earth's atmosphere. So 99% of all stars brighter than about 11th magnitude were mapped by the Hipparcos mission. A very successful mission, even though it had such difficult issues to deal with. The next one I want to talk about is Shoemaker. It was originally called just NearEarth Asteroid Reconnaissance Mission, and then when Gene Shoemaker was killed in an auto accident, I think it was in Australia or New Zealand, they also named this satellite after him, or this spacecraft after him. It was supposed to go up and examine Matilda 1 or 2, an asteroid, big asteroid. But unfortunately, well, everything on this one, most of the time these satellites, if something was going to go wrong, it happened in the first few hours. But in this case, NEAR did a good job. It went out, it flew by Eros, the satellite Eros, took some great pictures, came back, flung around the Earth, picked up some speed, flung around the Earth, took some pictures of Earth, headed back out. It was supposed to turn around and fire its main rocket for 15 minutes to slow it down so it could start matching speed and trajectory with Matilda. But unfortunately, the burn lasted less than 2 seconds. And so that wasn't good. And then right after that, they lost communications with the thing. And for over 27 hours, by the time they were able to reestablish communication, they realized that it was more than 1,800 miles off course. And also it was trying to right itself. It was wildly spinning. And 600,000 small thruster firings pretty much drained most of its fuel reserves. So it was like, oh well, there's another one for the scrap heap. But the engineers came up with an idea. Well, there's no way we can get it back to Matilda. But you know what? The way it's going, if we do this just right, maybe we can get it back to that asteroid we passed the first time, Eros. And so they were able to get it to burn. Oh, I forgot about this. Another problem they had, the solar, because it was spinning around like crazy, the solar panels were not being aimed at the sun, so they couldn't recharge the batteries. And so they were just having all kinds of trouble. They thought they were going to have to scrap it, but they finally did manage to regain control, be able to orient the so that they could recharge the batteries. And they decided, well, Matilda's out of the question, let's go to Eros instead. I told you already, 1,800 miles off course. So they scrubbed the mission to Matilda. Why aren't you working? So they went back to Eros. This time, finally, something went right. The main engine fired perfectly. And so they were out kind of in front of it. The engine burned. It went slower and slower. It creeped up on Eros. It returned more than 160,000 images of that asteroid. And then eventually they were able to actually land this probe on the surface of Eros. In fact, as it landed, let's see, on February 12, 2001, mission controllers landed the craft on the asteroid. Just before it landed, it was able to send back a picture that resolved details as small as 0.4 inches, which is 1 centimeter across. Really tiny stuff. Before that, it had taken all these pictures. Some boulders were as big as a city block. Others, just and everything in between. So it was fascinating to see all the pictures that came back from that mission. Looked like it was hopeless, but they actually did all the mission goals. Wrong asteroid, but at least they did all the things they wanted to do. They explored an asteroid, and more, they never intended to land it on another asteroid. So that's important, because if we think about an asteroid that might eventually impact the Earth, the ability to land something on an asteroid might be very important. So the last craft I want to talk about is the Hubble Space Telescope. And most of you here probably remember when Hubble went up and how exciting we were all going to see all these wonderful pictures. They're going to learn what the Hubble constant really was. And this was going to be the telescope of all telescopes. Super highly polished mirror. They worked very hard figuring this mirror to be the most precisely polished mirror that had ever been done. This thing, if it was expanded to be the size of the Earth, the largest dip or the largest hill would only be about 6 inches if it was the size of the Earth. Can you imagine something that smooth? Just amazing. Unfortunately, they polished it really well, but it had been ground perfectly to the wrong specs. So it was figured. I mean, it was polished beautifully, but when they first ground it, it was just not shaped right. So if you did the same kind of idea, well, if you expanded the wrongly ground mirror up, now you've got the edges 35 feet down instead of a nice spheroid like it was supposed to be. The edges were more flattened out. And what that did, all the light would come in and bounce off in erratic directions and get focused, totally ruined the picture. So the first light was M100, and this is what it looked like. And it was so disappointing. I don't know if you've ever made a big purchase, got it home, and it didn't work. Or you bought a car and you drove it for a week, and suddenly your oil's all over the driveway, and you have all kind of problem, and your heart just sinks to your feet. Well, imagine everybody connected with this mission. When they got this first image back, it's like, oh, what happened? Well, they figured out that the mirror, now the backup mirror, of course, it was perfect. They did it right, but the one they sent up had problems. So this was first light M101, and then I said most of that stuff. Turn down edge equivalent to 35 feet if it was scaled up to be the size of the Earth. Now for comparison, I wanted to show you, so this is the Hubble image. This is a ground-based telescope image made by David Mallon at the Anglo-Australian Observatory. We could do a lot better from the ground. And to be fair though, this part here is like this part here. So, but you can see you know, these strings of stars are still visible in this image here too. So there wasn't much of an improvement. In fact, one of the scientists said, well, I could take pictures better than that with an 8-inch scope. And this is actually a picture of M101 made by Martin Germano with a 14.5-inch Newtonian, just an amateur image of 100. So not 101, but 100. So yeah, Hubble is in pretty sad shape. So enter COSTAR. And COSTAR stands for Corrective Optics Space Telescope Axial Replacement. I probably should have asked if anybody remembered what that meant. I could remember the corrective optics part, and that's as far as I could remember. So, huge improvement. Now we have, this is the original image, this is with the COSTAR edition. And you can see now, this was the Kitt Peak. That was the best image that Kitt Peak could do. And there's a little bit of the core there. Now you can see what Hubble does. This little part here is what Hubble returned. So a huge improvement. And everybody's seen, we could just do an hour presentation with nothing but Hubble pictures and nobody would be bored. They're always so beautiful. Hubble was just an amazing mission. Here's on this part here, this is a mosaic that Hubble did. Here's the core. And then here's a close-up of that core with the WIFPIC wide field planetary camera at full resolution. So it's just amazing what Hubble has done. So best laid plans. We all make plans, and oftentimes they don't go exactly as planned. Sometimes the plans work out actually better. You learn more sometimes when you make a mistake. But in the case of Hubble, you know, we were so excited about the images we got back. I remember going to astronomy clubs and everybody was just sick because of what happened. But all these space probes, we owe a huge debt of gratitude to the people who made these things possible. We don't realize it, but like the Mars Pathfinder missions, they were on Mars time, which was different than our time. The days were longer, and so they would work longer hours and sleep, and their bodies would get really out of whack because it was like 3 hours longer. So each day shifted by 3 hours, and you know, you'd get, sometimes I'm getting up in the middle of the night, sometimes I'm getting up in the morning, but they had to stay with it because they follow the rovers around when there was daylight, sunlight shining on the solar panels on the rovers. People spending all night trying to figure out, how do we fix this issue? How do we fix this problem? And I just wanted to say that there's just an amazing legacy. We owe a huge tribute of thanks to those who have worked the odd hours and the long time to help us understand the universe that God created, all the beautiful things that are out there, all the mysteries that we're trying to solve. What is out in space? And I had to give God a little glory. The heavens declare the glory of God. The skies proclaim the work of His hands, from Psalm 19. And I believe they really do. When I look up at the heavens, I see God's fingers, what He did, and what a beautiful universe He created for us. If you have any questions for me or Evan, or it's almost 9 o'clock, so you've been very patient. Thank you very much. Do you have any questions for either one of us? Drew?
Mariner was a great success. Is that due to some significant difference in that spacecraft, or something to do with the launch difference corrections?
The significant difference was primarily that all of them before that had failed, and they had learned. Every failure was something that they learned, and they learned a lot from it. It's one of the great quotes. I don't remember it specifically from NASA, but it's every time we failed, we did better. You know, I mean, it's a much more elegant quote if I knew it exactly. So every time they didn't do it right, as Einstein once said, we haven't failed today, we've learned one more way in which it won't work tomorrow. And so that's really what kept me going.
Does that increase a desire you might have for Ames or your own spacecraft?
I get that question a lot, actually, as somebody that's studied robotics and going into robotics. I'm a professor of robotics. And research these things and build, hopefully, robots for NASA. I am a huge proponent of manned spaceflight. We've had this conversation quite a bit this week. Robots can go and tell us where a great place is for us to go, but I'm so strong a believer in manned space exploration. So, anybody else?
Me, on the other hand, I'd like to see us just send robots, because you don't have to send air and life support and all the rest of it, plus risking people. Evan sent me, I was surprised, he sent me a link to a list of fatalities and injuries that have happened in space programs, not only in the United States, but in Russia, Japan, other places. A lot of people have lost their lives trying to explore outer space.
And that is a point, so their lives that they put so valiantly towards human space exploration, it would be for naught if we don't continue the legacy in which so many have gone before us to do. So, get a question?
How can you cover Skylab and how bad is that program?
There's only so much we talk about in an hour.
I have to pick the ones, you know.
Yeah.
Yeah, Skylab was, oh man, it had so many problems getting up there and in orbit and stuff, but it returned a huge amount of information. We learned so much about the sun. We learned all kinds of good stuff. And yeah, there's...
Well, I could give a comment on that. But these two guys are volunteers who worked hours and hours to get this presentation ready, and we're always ready to hear another person give it.
Sure, I tell you what, in the last 2 weeks, I did the lecture last week at Adele also at NASA, and I have several friends at NASA that have come from the aerospace program here and from others at Kansas State. They have found a new place to dump their extra stuff. I have gigabytes upon gigabytes upon gigabytes of information that they have sent me, and just sorting through it is astronomical. We can use that pun, if you will. Just trying to figure it all out where it all goes. There is hours of stuff just to talk about the probes that I had on that list there. And we can even leave Cosmos off of that. I mean, there's 2,441 of those. So it's, you know, even Skylab, we could talk about Skylab. Those of you that remember Armageddon, where the Russians beat on the space station, that's actually how they did it. And not Skylab, but in Mir, excuse me, that's actually how they fix things in Mir, which hammers my favorite tool, so it makes sense. Any other questions?
Galileo. Well, you know, Galileo's main antenna failed to deploy, and so they had to come up with a way to tape record all the data as it's passing around Jupiter, and then slowly send it back. You know, you think your connection time to the internet is slow? Right. You got nothing.
34 bits, I think, or 134 bits or something like that is what Galileo was relegated.
Just terrible.
Yeah, we could have talked about that.
Yeah, true.
Kind of a two-part question.
Sure.
The solar panels that were used in that era, what efficiency, 10-15%?
Oh, no, 3, 2.5, 3. Oh, yeah. It's only been gallium arsenide space grade or aerospace grade solar panels now
20?
16? Yeah. And we're talking $100,000 a square foot or more.
In general,
So.
the other part of it is, I think of starting the car in January at 20 below. You have oil and steel.
Right.
And obviously they start out with a very different mindset to begin with.
Absolutely.
I mean, what is it, Teflon, and what basic...
There's all kinds of different things, and that's actually the presumed reason that the Galileo main field antenna failed, or the high gain antenna failed, was after Challenger, it was put in storage. And because the space program was put off for so long, and they think that the lubricants actually evaporated in storage, and that's why the antenna couldn't open. They hammered it. They hammered it over 20,000 times, the motors back and forth trying to get the main gain, or the high gain antenna to open.
So they do use lubricants.
They do. I don't honestly have any idea what they are. That's probably something I can find out, but I don't know. Well, and it's James Webb. It's an infrared interferometer. Everything puts out infrared wavelength. So even a telescope puts out infrared wavelength. So it has to be colder than the things that it's doing, which is why its heat shield is so huge. I believe in it. I can't remember exactly, but I think each layer that actually drops the temperature 12 degrees. Its operating temperature is negative 364 Fahrenheit. Right, it's incomprehensible, so there's a question. Yeah.
So have a lot of these malfunctions been explained, or are they just random phenomena?
No, some of them have, as far as whether we can quantify it as a lot.
We used to joke a lot about Mars because, and remember the Mariner returned images of, I remember those, the first images of Mars, craters, and thought, well, that's so much for life on Mars. But they returned this face on Mars. Remember that picture of the face on Mars? I thought, you know, the Martians don't want us to see them. They're shooting down our missions. We had they call it the Mars curse.
Right, yeah, they did. There was 5 missions, I think, lost there.
Yeah.
Some of them were very, very simple things. Lander crashed because they programmed it, there was a conversion error between metric and English, and they programmed it in meters and measured it in feet, and so it flew, it thought it had to fly 4 times further, and so it kind of buried when it hit Mars. So, but questions?
The Science Center still has Hubble film listed on their website.
Okay.
It's pretty neat. It's really worthwhile.
Yeah, well, that's something I haven't got a chance to do yet, so soon. Now that school's over and the lectures are over, I might have a chance to get down there, so it's great. Drew?
I've heard that pictures from 1965, Mars, we're getting the first crater pictures and all this, that we are starting to lose some of these things because we're not transferring the data to newer technologies. How much, or I don't know, maybe you didn't run across this, but how much of this data have we not gone through, have we not accessed?
Actually, I haven't run across it in my research, but I grew up about an hour and a half from the Cosmosphere in Hutchinson, Kansas, which is actually where NASA's largest archive vault is. It's in a huge salt mine because the temperature's always 50 degrees. There's no moisture, and so they don't have to worry about some of this stuff. It's a naturally made huge vault. And there's quite a bit of it. I mean, when you think about what was one of the 160,000 images of that one asteroid, and Hubble's turned in millions of pictures, and it's just the man-hours are incomprehensible to be able to go through all of them. So yeah, and I can imagine, especially on the old acetate films and stuff like that, that they're deteriorating to the point where we will lose them. So, I don't know of any large project to go through to actually digitize that stuff. So that'd be something interesting to look up on. Anything else? All right, well, it's great to see so many people come out to see about robots in space. It was fantastic to be able to talk to you guys. Thanks a lot.
Oh yeah, that's the other thing. We kind of forgot to give our blurb to Nick, and
yes.
So we'll have to do that. What he put in there about our talk maybe next year. That'll be part 2.
Fantastic job.
Yeah.
By the way,
he said, "Come on, guys, I need this," and I told him I'll do it, and then got busy and forgot. And so sorry, Nick. Thank you, guys.